Hey there, everybody. I don't know why this is doing this little glitchy thing, but I guess there'll just always be some computer problem in this class. At least this time it's not forwarding itself on me and it's going through, so I'll be able to take my time with these slides a bit. I saw on the class website people have started taking quiz 1. Now the video for quiz 1 I actually was just able to upload before class today. This is a video for chapter 2. I will hopefully be able to load up after class today. Usually it should be quicker than that, and so but those are loaded up for if you ever want to watch those videos at some point. Well, any general questions before I just start talking about chapter 2? Yeah.
I just sent an email over the weekend. I had a question on one of the terminology questions.
All right. Well, over a holiday weekend, or like any weekend, I often won't be checking emails, but I will check when I get back to my office. All right. Don't check emails over the weekends if I can help it. You guys know how that is, right? Any other general questions? All right. All right, the atmosphere. Well, this chapter doesn't cover everything about the atmosphere. It actually just covers some aspects of the atmosphere. This picture here taken from International Space Station. The point of this picture is to just basically show you kind of that from that height you could see basically where that atmosphere ends, especially as far as the component that are active that we care about, which is mostly the weather areas. Now, of course, we'll talk about areas of the atmosphere outside of clouds and whatnot. That's all the stuff we'll be talking about today. It's actually pretty quick, the stuff we'll be talking about. Air quality. The beginning of this chapter talks a lot about different countries and their air quality or lack therein. I don't know if people have traveled a lot. When I went to China, it was actually before they started cleaning up. They started cleaning up about 2007 because they wanted things to be cleaner before the 2008 Olympics. And so they actually passed a bunch of environmental laws. But these environmental laws were mostly had to do with just Beijing, because that's where the Olympics were being held. Many countries around the world, especially if they're rapidly developing, well, there's this kind of assumed phase of development countries go through where it's like, well, in your early industrialization, there'll just be a lot of pollution. There'll just be a lot of polluting. That's just the way it happens. More recent thought on this, people have pushed for what's often called leapfrog development, which is, well, if we know that there's a polluting phase, isn't some way we could just kind of like jump past that and just go to the less polluting phase? And that's basically what China did by trying to change a number of their environmental laws. When I was there, the air quality was like, well, I don't smoke, but people who I were traveling with, they said it was like smoking a pack of cigarettes a day, just breathing the air. India has actually surpassed China as far as poor air quality. I don't know if people have traveled to India either. In India, the pollution, it's worse partially because there's a lot of particulates in the atmosphere, a lot of burning. If you guys ever travel the world, most places in the world don't have good garbage pickup. And so what people might do, like if you could just picture a business that's on like just a mall, right? What they'll usually do is in the mornings, they will get up and they'll sweep kind of all the debris or whatever that is kind of accumulated near their store. Could be like a branch and some leaves, could just be plastic bags and whatever garbage people have. They sweep it into a little pile and then set it on fire. And so in the morning, often in these cities, there's all these little fires going everywhere. And so the pollution, well, in India, it's more of that kind of thing. China, it's kind of interesting because, well, we all get our heating from different places, right? In Minnesota, there's a fair amount of natural gas. in China, the most common way to heat is through these little coal bricks. It's kind of interesting because there'll be a person will come along on a bike with a bunch on their back, and there'll be these round things with these holes in them, and you just buy it and you put it in your oven and you use it for heating, for cooking. People have ever cooked with or gone to a restaurant where it's coal fired? Like, it tastes good, but per unit of energy you get, coal releases twice as many carbon emissions than natural gas, right? So it's a lot more polluting. Plus, the thing with coal is, when you're burning coal, you're usually burning whatever was kind of mixed in with it, and there's different grades of coal. And some countries have like really great grades of coal. Britain is a kind of a classic example where when they industrialized, they had lots of pollution, but their coal was actually very clean burning. Unfortunately, the coal in China and India, for that matter, tends to be the less clean kind, but it is very cheap and very plentiful. Let's see, anything else? China, India. Oh, and this picture from the book. So he vacuumed the atmosphere, well, for 100 consecutive days, and collected everything that he took out of there and made a brick out of it, just to show how much stuff basically you could be breathing in, right? If you're in an area that's polluted. All right. Oh, I should also say, although China still has a lot of pollution problems, they are, like I said, trying to do this leapfrog development of, let's just jump past this polluting. Much of Europe polluted themselves for hundreds of years through industrialization. China has been industrializing for like maybe 50 years, so they're hoping to jump. Yeah.
You said there's different grades of coal. What kind of coal was here in the U.S.?
Being a big country, we actually have a good variety. We have a fair amount of the good burning coal, especially kind of in our area, Minnesota, and I would say more the adjacent states. In Appalachia, it tends to be a little bit.
That's where I was kind of thinking more.
More impurities kind of mixed in it, and that's the thing. It's just whatever random thing. As I'm sure you may all know, fossil fuels were mostly all formed from the same time period. Something like 250 million years ago, the Earth was very swampy. Lots of organic material grew and then, buried. And that's why they're called fossil fuels, right? So coal, the solid stuff, oil, liquid, natural gas, obviously, gas component that are still left. If we want to see what an example of a place without an atmosphere looks like, moon is a good classic example. Very, very hot under the sun. Very, very cold when you're not under the sun. And also, one interesting thing that they found out when they went to the moon, the lunar surface that, we were quite unsure what it was going to exactly be like. The moon is what happens if you have a whole bunch of rock that keep on slamming into it without any atmosphere to burn up meteorites and stuff. And so, if you will, when they took a magnifying glass to the kind of soil, it's all these really jagged, sharp edges of little particles. And so they actually really tore away at the suits much more quickly than the astronauts predicted. And the suits needed to be replaced very quickly because each of these were like a little tiny saw at each little crevice and whatnot. Because they're jagged because there's no weathering, right? There's no rain, there's no sleet, there's no hail, there's no snow, there's no wind. All right, types of gases in the atmosphere, right? Permanent gases, these are the gases that don't change a lot, right? They change somewhat through time, but not much in the human lifespan, right? So for example, the percentage of oxygen in the atmosphere has changed throughout Earth's history. There have been times when there's hardly any oxygen in there. There are times when there is far more oxygen in the air. In fact, if you look at the fossil record of the time frames that there were very large insects, something about the structure of an insect means that it has trouble getting oxygen to its body parts if it gets too big. And so that's why insects, they've kind of maximized out how much size they could get for how much oxygen we have in that atmosphere. Times when there was a lot more oxygen, insects were able to grow to be quite large. But you know, there have been times when there was enough oxygen to breathe, but not enough oxygen for fire to spontaneously combust. If you can imagine what humanity would have been like if we had never been able to use fire, you know? But this is one of the reasons why when you see your Jurassic Park movies, you know, and a big dinosaur is running around, that dinosaur would be out of breath and passed out so fast because there's not enough oxygen in the air compared to how much there was during the dinosaur days. So say that next time you see one of those dinosaur movies. All right, permanent gases, variable gases. As the name suggests, variable gases are gases that tend to go up and down a bit more rapidly. We'll go through these specifics here. Greenhouse gases, gases that absorb and emit heat. Well, like I said, we'll actually talk about each of these gases in turn. Nitrogen being the primary component of a lot of fertilizers, also of a lot of bombs. That's part of the reason why you hear randomly people making, bomb out of fertilizer, right? There was a long time ago that we did not know how to take nitrogen directly out of the atmosphere, and there were nitrogen mines and mining boom towns in places. But then when we figured out, well, it's most of the air, so we can actually just get it from anywhere if we just get it out of the air. Much less expensive than mining. Oxygen, argon, neon, helium. You might read news stories every now and then about how we're running out of helium. We're not really running out, but it's getting more and more difficult to get because people use it for balloons and things, and then it's just kind of like gone in the atmosphere, right? Rises up to the upper level of our atmosphere, but you have to mine it. You have to go find it in pockets and rocks and stuff. So are we running out? It's like, well, we're using it up. Variable greenhouse gases. Right? Variable meaning, well, these are in the atmosphere different amounts, kind of depending on things that humans do, right? Especially the ones that are made by humans, CFCs and HFCs. Well, there are, as you can imagine, sources of these different gases, and there are sinks of the different gases, right? Sinks can be all kinds of things, right? Big bodies of water can absorb different gases. Source of gases, of course, volcanoes, right? But although volcanoes are, well, they're great big kind of amazing things to see, the amount of gases that they actually release is not that much. And the sulfur that can be in their plumes and whatnot, when this mixes with rain, it can cause acid rain. But the natural sources of acid rain, very small as far as the time period that it has an effect, and the geographic location usually having to be pretty near actual volcano that is currently emitting a bunch of gas. Most of the gases that are released, especially global warming gases, those are more connected with humans and what humans are doing. Let's see. I don't think I want to talk about every single one of these gases. Well, actually, we'll talk about a couple of them specifically as we go on. Aerosols in the atmosphere, microscopic solid or liquid particles suspended in the atmosphere. Crowd droplets, usually these are, well, you have inside clouds, you have condensation nuclei, which raindrops form from. There's microscopic. But that's why you can actually, sometimes you could seed a cloud to get it to rain. If you have minute particles, you go on a plane over it and you just dump a bunch, they'll grab onto the cloud droplets and you could get rain where you wouldn't have otherwise. There's not a lot of that done these days, but sometimes. They do more of that in China than elsewhere. Common aerosols. Again, just picture very, very small particles, right? Weight of atmospheric pressure. Well, when you're watching the news and maybe watching the weather, you may hear them talk about high pressure systems, low pressure systems. We'll talk more about weather in general in a future chapter. But what this means is, well, if there's a high pressure system that is above you, pressure pushing down, that means one of two things. That either means that air above you is heavier because of the stuff that's in it, like a lot of clouds with a lot of moisture, for example. If that moves above you, well, then that's pressure. Some people will be sensitive to these pressure systems and maybe get a headache and stuff. I don't know if you ever heard people talk about that. Low pressure. Well, low pressure is when the air mass above you doesn't have much going on. Low pressure is also, well, if the air is just kind of rising where you are, it's very low pressure because the air is going up, maybe coming down elsewhere, and then where that air is coming down, they will have a higher pressure, right? It's kind of a simple concept. Just another picture from the book showing you just a visual of where the mass of our atmosphere is. And to get examples from the book of pressure, if it helps to think about underwater, and the further down you go, I don't know if people dive much, but the further down you go, the more under pressure you are. The higher up, the less pressure. Same is true if you're going up a mountain, right? Another thing that's true is, well, usually the temperature goes down as you go up in elevation, right? So as you go up, right, there's less particles on top, meaning less weight, right? And then as you go up, there's what's called the normal lapse rate, which is how much the temperature changes specifically. It's a pretty easy, this is the reason why mountains around the world will often have different ecosystems relatively near each other, because as you go up in elevation, you could plant different crops, you could have different types of housing, all kinds of different changes. Now this pressure, of course, like I said, well, we're used to it, obviously, right? We wouldn't exist if we had a strong effect of these pressure systems. But sometimes, if people are sensitive, they can get headaches and feel sick and whatnot. So the layered atmosphere. As you can see, the different layers of the atmosphere are largely defined by temperature changes within those different levels, right? And so in the atmosphere, as far as humans exist that are within mountains and stuff, you have a normal temperature change on average as you go up. But this has lots of ups and downs in the atmosphere, kind of depending on what's going on, right? Areas of the atmosphere that are in the high atmosphere that are getting a lot of interstellar radiation, those particles up there are being basically fried just all the time. And so that tends to be warmer. So the four main layers of our atmosphere. Talk a little bit about each one. Well, there's a section on our book talking about how we monitor all this stuff. I'm not going to go through every single thing, but everything we have that goes different places, use that to monitor. Let's see, is there anything I can really point out about all this? We do less of the hot air balloons than we used to, and we're doing more drone stuff. I think that's the main kind of difference through time. Because satellites we've been using for quite a few years, of course. Ships and buoys, aircrafts. Layers of the atmosphere. Again, just a picture from our book. Again, ionosphere, right? This is when we have interstellar radiation coming in, right? Not just from the sun, but all other suns of the universe are sending out radiation. And if we did not have an upper atmosphere that was blocking it, or I should say absorbing, well, we would all be fried. Even though this is a part of the atmosphere that we don't really interact with, it's a very important part of the atmosphere, right? See, what else would I point out? Mesosphere, where meteors and comets, well, comets might not burn up, but meteorites burn up. If you see a meteor fall in the sky and it shines. I think that's the main thing to show for these. I'm not going to go through every single interaction of the atmosphere. Troposphere, you'll see all these different terms with a pause for where they end. So you'll have a tropopause. Oh, here we go, environmental lapse rate. I mentioned this earlier. This is, the rate that the temperature decreases as you go up. It's pretty easy to calculate. There is some differentiation depending on how near or far away you are from the equator, because the atmosphere is actually a bit thicker around the equator. I say a bit? A good amount thicker than it is, say, around the poles. Temperature inversions. Well, that is the case where, as I said, normally as you go up, temperature decreases, but sometimes weather systems and whatnot can kind of make temperature systems stuck. I think there's some visuals I got here. Right, you'll have trapped air. The main examples from the textbook are pollutants and whatnot, especially if you have an area with a lot of pollutants and they're kind of trapped. LA was very famous for this, kind of having a smog zone that would kind of never go away. I would say internationally, Mexico City is one of the big examples of that, mostly because Mexico City itself is kind of a bit in a pit for a couple of different reasons, but it's higher elevations surrounding Mexico City, and so the industrial activity that happens in Mexico City can often be just stuck there. Other places have this happen too. So then we don't have the normal lapse rate anymore if we have this happen. If we have a temperature inversion, we have other things going on. Farms will often put things like this out in an attempt to try to break up the atmosphere and get it back to the normal lapse rate, because you want to have very predictable temperatures and weather for your plants if you can. You could basically see where the two different layers of the atmosphere here kind of come together. This is a classic sense of you have a lot of evaporation, right? And so you have clouds building, but they can't really battle much through the layer of the atmosphere. And so they'll just extend this way. And so if you see like a big thunderhead, something like that, that will be this kind of scenario. Tropopause. Actually, this image here is better. So you can see the atmosphere is actually quite a bit thicker around the equator. A number of different reasons. One of the main ones being it's quite a bit warmer. You have thermal expansion. You actually have this around bodies of water as well. Usually tend to be warmer around the equator. Kind of makes a lot of sense. But as you can see, we have on average 11 miles, on average 5 miles. So it's a good amount different. Stratosphere contains highest concentrations of ozone in the atmosphere. This chapter talks a lot about ozone and the ozone shield. There's lots of news stories for a good long time about the hole in the ozone layer. Don't know if people have heard about that before. Um, well, ozone is one of those kind of unique things. Ozone is O3, O3. So three oxygens stuck together, right? We breathe O2, right? Seems very similar, but if you try to breathe in O3, well, your body is not evolved for it. So it would be like trying to breathe out of the tail of a car. When that's one of the big ironies actually is, well, humans created CFCs, a chemical which is very useful in industrial processes and refrigeration, things like that. But when we made them, we didn't know that they basically go and when they interact with O3, ozone, they break it apart. Now O3 is the kind that blocks interstellar radiation, right? O2 and O1 do not. So we're releasing this, and scientists, not knowing anything about that, just checking out the atmosphere, saw that around the poles especially, there was a hole in the ozone. And what that meant was a couple of countries that are kind of far to the south, because the southern one was actually a lot bigger, they started getting higher incidences of skin cancer, especially Australia. And while it was a scientific mystery of what was going on, it actually took a long time to piece together that it was stuff that we're making that's breaking it apart. Well, and like I said, it's a big irony because ozone, we create it all the time. O3, it is what's coming out of your tailpipe. Industrial processes create O3 just in the wrong place. And by the time the ozone that we create would get anywhere in the atmosphere, it would have been broken down already. So if there was some way we could just take what we create and put it in the right place, instead what we did was, well, outlawed CFCs. It was the kind of more developed countries that were making it all that first outlawed it. And then other countries also phased it in because this was seen as kind of a global problem. And the good news is the ozone hole actually has been decreasing through time. Even though CFCs, when we make them, they can float around the atmosphere for 1,000 years. But they start getting broke down mostly pretty quickly. And so, well, that's kind of the end of this chapter talks about the good effects of environmental regulations and how this is one of the rare examples of international cooperation. See the area here with ozone. I basically just talked through a bunch of this stuff. Ultraviolet radiation, it's what's getting taken up by the ozone. Mesosphere, that's where in the graph it was showing where the meteors vaporize. Thermosphere, has anyone ever seen an aurora? Ever seen an aurora? But yeah, where was it?
I was down in Albert Lee like 15 years ago. There was just some weird random storm that had happened that stuff was appearing in southern Minnesota for some reason.
I think I might have seen that same one because it was about the same amount of time ago. I was just in the backyard of a friend's house, and all of a sudden it was the Northern Lights. I think there's a picture somewhere. When I saw it, it was greener. This is what someone took a picture from the ground. This is actually from a space station looking down at, but when I saw it, it was closer to this color. I've also seen it a couple times. I've gone to Alaska a few times. Come to see it there. Will common if you're lucky. All right, gotta back up here. I went too far forward. Where did I go? Oh yeah, auroras, also often called the Northern Lights. Well, gas molecules energized by charged particles. Solar wind, well, the sun is constantly shooting out rays, and it's also shooting out particles. Sometimes there are huge solar flares that, well, if Earth would have been in their path, we'd be fried. Just kind of happens as normal things that the sun does. We fortunate to not have gotten hit by any. Well, part of the reason you're going to see the northern and southern lights closer to like Alaska or closer to the poles is that's basically where they're all pulled in, where all these particles, because they are the poles, there are magnetic poles. Air pollution. Definitions of air pollution: harmful concentration of gases or aerosols in the atmosphere. Most pollutants are, anthro, meaning human, meaning humans are creating these, humans are putting them in places. Even things that are natural phenomena, like wildfires, that's nothing unnatural about fires and wildfires, except for, well, humans are kind of managing or not managing large areas of forest, and kind of the things we do or don't do can contribute to these types of fires. So for example, you could have a place like in California, Southern California. It's a pretty dry climate, but especially in the 50s and 60s, you had a lot of people moving there, and people moving there wanted to have a suburban home like they had back in Minnesota or elsewhere. So they're like, well, let's have a lawn, I'll just water it, and I'll have some trees, and I'll build my house and a nice porch and all this stuff. Well, anytime someone doesn't water for a little bit of time, all that stuff dries out super fast. And it's a whole bunch of organic material in a landscape that normally just has kind of like sand and rocks. And so, well, basically, humans through suburbanization created a whole bunch of stuff to catch on fire. And so that's what happens, because there's all kinds of times people will, a house gets foreclosed upon, no one's paying attention to it, the grass and the bushes all dry out and die. It's like just made for a fire. Let's see. I feel like I've talked about most of this stuff. Primary and secondary pollutants. Well, primary pollutant is, as it sounds, enters directly from the source. Carbon monoxide, again, something else that comes out of your tailpipe. We know where that comes from. We go right to your tailpipe, and it's like, oh, that's exactly where that is coming from. Secondary pollutants formed in the air or water through chemical reactions among primary pollutants. So this is when, you have a pollutant, let's say, even chlorofluorocarbons as an example. Well, that thing itself, when it was tested, when we developed it, it was inert, wasn't harmful, seemed like it was a perfect thing to invent to use, but then its effect on other things is the problem, right? Pollutants and sources. Let's see, I'm not going to go over every single one of these. Any of these important to know? Nah, I'm not going to go through every one. Well, we'll talk a little bit more about acid rain. Acid rain, yes, it can happen next to a volcano. If a volcano is going and emitting gas. But of course, what is more common is when we're burning stuff, like if you are burning some coal and some of the impurities in that are sulfur, which just happens. Sulfur is just in the ground. Digging up coal, could be some sulfur with it basically. Well, when you burn it, that sulfur is released into the air, mixes with rain clouds, can create acid rain. This is one of the reasons why, well, if you go on any trips to Europe, you'll often see that they will have carted in their big statues, especially if they're marble, because the acid rain can degrade this, and it wasn't because there's mountains in the region. This is from when Europe went through their whole industrialization, and they were burning tons of coal, and even though they had relatively cleaner coal, if you burn that much of it, you're releasing so much sulfur. And Russia was especially bad, actually, because when they industrialized, they really gave no thought to the environment. And so before they even noticed, a whole bunch of statues and whatnot that were historical just had dissolved their faces off before people kind of noticed what was happening. As you can imagine, it also damages trees and whatever else. So a map of acid rain in the US and Canada. Map on that side is from 1990. This one is from 2010. As you can see, there's some major changes that happened between 1990 and 2010. Acid rain decreased a lot. I don't know if people know the geography of the US very much, but this whole area here is basically the industrial heart of America. This is where, in our early industrialization, this is where like all of our factories and everything were. Automobile plants, all that stuff, right? And so industry needs power. There's burning of a lot of fossil fuels, and so there's quite a bit of acid rain. Now, a number of things have happened. Environmental regulations kind of came in. Now, there are people who will argue that environmental regulations increase costs, right? And so, if you have, like Michigan here has covered a good amount. If you have Detroit, Michigan making cars that are for sale on the international market, right? And let's say you have a car that is being made in Japan, right? Now, historically, in Japan, they actually usually had stronger regulations about their environment. And so what that would mean is their cars would be slightly more expensive, technically. But Japan felt that it was worth the price because there's the added costs of not just your environment, but human health from having acid rain and having a lot of pollution and whatnot. Well, through time, North America started having laws passed as well. Something else also happened that the book doesn't talk about that much is this is actually the time frame that we globalized our manufacturing quite a bit. And so a lot of these manufacturing, if you ever read news stories about manufacturing in the past 10 years or even 20 years, you'll hear them talk about manufacturing jobs going away in general. And that is true. Our unemployment rate is still pretty darn small, so I don't know if the economy has taken a hit from that. And we've started to get manufacturing jobs that are back. This is only the past couple of years. A lot of this is because a lot of our industrial processes don't need to pollute as much anymore. So things like 3D printing, you don't have a lot of pollutants when you're just kind of 3D printing your thing, and that's industrial production. So kind of cleaner industries have come back a bit, put it that way. Let's see here. Already mentioned ozone, O3. We make it in cities, industrial processes. So if you're stuck in traffic and you're just feeling just really crappy, it's not just because it sucks to be stuck in traffic. It can be you're sitting with all these gases that all of our cars are making. Particulate matter. Again, these are things like aerosols suspended in the atmosphere, and this does happen naturally. So, for example, well, near the oceans, I don't know if you've ever been to the ocean, but you could smell the ocean before you're there, right? Well, that's little particulates of salts and whatnot that are in the water, that are in the air, and those actually, well, when they get up to the clouds, those can be condensation nuclei for rain. So very often, next to the sea, you'll get sometimes extra rain because those particles are in the air. Of course, there's lots of stuff that we're putting in the air right now, mostly through burning the things, right? Fossil fuels, vegetation. What does that mean? Well, there's a lot of vegetation that's being burnt all the time. Slash and burn agriculture, very apt name for what it is. We'll talk about that as we get into our section on rainforests and stuff. The book includes animal dung. Why is that? You may not think that that's a big source of environmental contamination, but worldwide, animal dung is often used for heat, for burning, because there's a lot of it, and it's pretty cheap. And so there are plenty of places around the world where they'll just burn that. The book has these pictures as an example of, well, this is a person who's going up in elevation, up a mountain in Hawaii, right? And the further up they go, the less particulates there are in the atmosphere. And so they use the example of, if you hold your finger out and put it over the sun, how much kind of stuff can you see past? Particulate matter, in this map you could see, as I said, places that have a lot more of this type of burn-in here and there. Well, similar to when I talked about temperature inversions and how you could have these air masses that are stuck, I also mentioned that often these can be affected by pollution, these can be reinforced by pollution, and they can make pollution worse if your air isn't able to circulate. Like I said, some cities, kind of depending on their geography, especially if they're surrounded by mountains, if they have a lot of industry, will find that, oh, these don't blow away and we're just kind of getting a buildup of a lot of toxins. Those are usually the first places in the US, at least, that had environmental laws because they were so overwhelmed with how bad the environment could be in those locations. Just some visuals of temperature inversions related to smog. So you can see why a place that has this going on a lot would want to have some quick environmental laws. Places that are a bit more like this are a bit slower to kind of see the problems. Air quality index. I'm not going to go through every layer of oh, that's right. The end of this chapter talks a lot about environmental regulations, especially in regard to air pollutants. I would say the 60s and the 70s are kind of a big time that people started kind of getting conscious of these things. Like I said, there's this argument that reducing emissions makes things more expensive. I personally think that, well, you could actually get by that by, if we have environmental regulations, not having trade with countries that don't, so that countries aren't making extra money by poisoning their own people, right? I don't know if we'll ever see that come into action, but that's something that would work. So air pollution trends in the US. Although our population is increasing and the wealth in the US is also increasing, the amounts of goods and services we make has been going up this whole time frame. Yet the pollutants that we associate with making all these things have been going down. Well, because piece by piece we're having environmental laws that make it so that you can't pollute. So this is kind of in the correct direction, I would say, that we've been going for a while. Now, of course, there's been lots of ups and downs over the pandemic. Where will the future go? Hopefully continued in the right direction. We talked about CFCs a bit. CFCs often, well, because people don't like to say chlorofluorocarbons, and so they just say CFCs, but they're the same thing. They're, again, these things that break apart the ozone, but that seem completely inert on their own. Well, I think I already talked about this a little bit. Well, it wasn't until the 70s that really enough scientists came together to point out that it really seemed that the CFCs we were making were destroying our ozone, making a hole in the ozone shield. As you saw from that picture, ozone shield was thinning dramatically. This is a good visual of just how CFCs break up. Again, O3 is ozone, right? If you have a CFC come in and they grab one of those, well, then we have O2, which, is breathable, doesn't help us in the upper atmosphere too much. And those are usually broken apart too, so we just have oxygen just as a 1 or 2. It's not really blocking interstellar radiation. Actually, there was just a new news story about this last week, but it does look like the hole in the ozone shield is shrinking through time. It is self-healing to some extent, but it will take quite a while before all CFCs are gone. UV index map. These aren't really used for popular consumption a lot, just because people usually don't think about it. If you're going to go out on the beach, you probably don't look up the UV index and see if there's where you're going to the beach has less protection from UV. And again, that's just from the flow of the air, the flow of how amount of ozone is there above any one area. Kind of has ups and downs. If you did happen to want to go out to the beach and look this up, you might save yourself a burn or not. So Montreal Protocol, as you can see, it was actually relatively recent that we started phasing out CFCs. And then it took a while, once we started phasing them out, for it to start having an actual effect in the upper atmosphere. But as I said, now it's been like 20, 22, 23 years. And it does appear that it will stabilize. Let's see what else. Hydrofluorocarbons. Those were designed to replace CFCs. They're not as bad, but they are greenhouse gases. So now those are being phased out. I don't think they've said what the next thing they're going to come up with. Hopefully it's not, something that makes us all zombies or something, I guess. All right. Left you guys plenty of time to work on some questions today, but I'm going to form your groups. All right. Going to have you work on questions from the textbook 1, 3, 4, and 5. I'm going to have you skip 2. Actually, I'm not going to form you guys in groups. I'm going to have you guys form your own groups, but in size between 4 to 6 people per group. 4 to 6 people per group. In the same scenario that we did last time, we have one piece of paper, everyone's names on it. If you're off an island, feel free to move around and meet up with people. But we'll work on these questions. You'll turn it in. I'll grade it immediately. If you have one that's wrong, you can rework it if there's time left in the class. Raise your hand if you've got any questions. But self-select. You could be in big groups up to 6. Up to 6 people per group.